kind of start digging into this idea of the postulates. All right, so the first thing I want to talk about, it's not really a postulate so much, but it's an important property of matter, of all quantum mechanical objects. So I'm going to call it the zeroth postulate. It's not the first. But it's the idea of wave-particle duality. Right? What we're going to find, what does this mean that something's dual wave and particle? That means depending on how we observe it, how we interact with it, an object, say electron, or light particle, whatever you want, an atom, anything you think of. Depending on how we act with it, it'll act like a wave or it'll act like a particle. Right? So what do we mean by that? Well, we got to think about what are the characteristics of a particle and a wave. So a particle, right, which you think like a billiard ball, right, an object with a size. It has a mass, of course, and a size. But let's think about its physics, right? What does a particle have? Well, it has a position, right? So it can be defined by two variables, right? And we learned this from physics. One, it could be defined by its position. So the x vector, right, this is the position. And the momentum. Right? We'll use momentum in this class. We won't use, you might think, okay, well, maybe we can use velocity instead. Remember momentum, let me just remind you that for a particle, for a classical particle, so Newton says that P is the mass of the particle times the velocity. So, again, we can define any particle with these two. If we know its position and we know its momentum as a function of time, we can calculate its position anywhere, right? Because if I know its position, I know where it's at. If I know its momentum, I know which direction it's going and how fast it's going. So at any time, I can calculate its trajectory somewhere else. Okay, so a particle is defined by these two things. Right? It has, and what are some other properties it can have? Well, it can have energy. Right? You can have energy. Has some sort of energy. Right? And sometimes we say kinetic energy, right? Typically particles have a kinetic energy, a motion. Right? So kinetic energy. And it can also have potential. Right? Right? And the kinetic energy is 1/2 mv squared. And the potential energy, well, it depends on the potential. If it's gravitational or whatever, typically we just represent the potential as a function v, which takes in the vector x. All right, so it's a potential function. All right, there's going to be a different potential depending if the particle has gravity or if it's electromagnetic, right? If it's attracted to a charge, for instance, right, there's going to be a different potential for depending on the system. Okay, if we know these things, if we know the position, we know the momentum, and we know the energy, we can say everything about the particle. Right? It's all we need to know about, let's say, a gas, for instance. Right? An ideal gas or some billiard ball moving around. Right? We just need to know its energy, its position, and its momentum. And in fact, we don't even need to know its energy because you can define its kinetic energy. So I'm just going to redefine that the kinetic energy of the particle, right, is 1/2 mv squared. But it's not hard to just do a little bit of manipulation to show that this is p squared over 2m. Okay? So the kinetic energy of the particle is actually dependent on the magnitude of the momentum. Right? The faster the particle is moving, the higher its momentum, therefore it's higher kinetic energy. So the kinetic energy is proportional to p. So really, the only things that we need to know about a particle is its mass. Right? We need to know its mass, of course. We need to know how it interacts with the universe, whether it doesn't interact at all, or maybe it's attracted to something, right? That's what this determines, the potential. But if it doesn't have a potential, if it's a free particle in a vacuum just moving by itself, if we know its position and we know its momentum, we know everything about the particle. This is just Newton's laws. Okay, so what about a wave, though? What are the things that a wave are characterized by? Well, a wave has an amplitude, right? That's the peak of the height of the wave. We'll call that A. It has a wavelength, lambda, or a frequency, either one. We'll compare the two in a second. We'll call frequency V, or nu. Right? And it also has what's called a phase, which we'll call phi. And we can write a wave, a generic wave, we'll call f of x for a wave is a, for instance, cosine 2 pi over lambda x. All right, that's a wave. All right, it's just an oscillating motion of some material that has a wavelength or a frequency. It's got a phase. I forgot to add the phase to it. And an amplitude, right, which is how strong the wave is, right, the height of the wave. So, of course, you're going to ask the question, well, if we have a particle, what if a particle is like a wave, right? How do we relate wavelength and frequency and amplitude to particle numbers, right? Because I don't really have a kinetic energy here. I don't really have a potential. I don't really have anything that looks like the things that a particle has. But I have these two different types of classes of things that have physics, right? I can have a wave, something that's propagating in space, like a light particle, right? A light propagates like a wave, as we know. But we also have particles that move with x and p. All right, and one of the great things about one of the big discoveries of quantum mechanics is that objects, microscopic objects, mechanical objects, like electrons or atoms, you can view them in either view. You can look at them as if they're waves, or you can look at them as if they're particles, depending on your experiment. They show both properties. We'll see this over and over again in this class, but I just want to introduce this to you here. So any quantum mechanical object and I mean any, has both particle and wave-like properties. They both have wave-like properties. All right, and so one of the kind of early discoveries that people made is how to relate wavelengths of a particle, say, to its energy, right? So let's think if we have a particle like an atom or electron, and we want to think about its wavelength and its particle-like properties at the same time. How do we relate the two? If it's both, there must be some way to relate its particle properties to its wave properties. Because it's the same particle, it has the same energy regardless of which way you think of it. Right? The energy is always conserved whether it's a particle or a wave. You can fit energy into a wave by increasing its amplitude. The amplitude squared is dependent on the energy. And so if the amplitude is proportional to energy, then we can relate the kinetic energy of the particle to its amplitude as a wave. And a rich hermit French nobleman named Charles de Broglie. So he was a fail son of a old French royal family or noble family, and he spent his entire life hiding in his room doing physics experiments with his parents' money. And he comes up with a really, really lovely explanation to relate a particle's properties to its an object's particle properties to its wave properties. And so what he uses is very interesting. He says that, okay, so for light, and this was found out by Maxwell before, so in the 1800s, this is already known, that the energy contained by light or a field, is equal to the speed of light times its momentum. All right, so this is the field energy of an electric field, or a wave, if you will. Right? This is the wave momentum and the energy. But there's another relationship that helps us compare momentum for light by the fact that the wavelength of the light times the frequency of any wave is equal to the speed at which it propagates. And of course, for light, that light only propagates at one speed. It's the speed of light. Right, so this is the speed of light. Okay? So this is always true. This is a really important relationship to remember. The wave and the wavelength and its the frequency of a wave, which is how fast it goes through a period, and the wavelength of the wave, which is how long the period is in length. The product of those is c. They're inversely proportional to each other. Okay, so you can always convert between wavelength. I'll just write that. Wavelength again has units of meters. And frequency has units of per second, per time. Right? And you can always interconvert them with this formula. Right? It's very, very useful, as we'll see in a second. We have one more relationship that we can use. And if you go back to your notes when we talked about the black body, about Planck's law and the black body radiation, Max Planck realizes something very interesting. Remember that I said that what Max Planck said is that the energy of the light being emitted from a black body is equal to some number n times some constant h times its frequency. So n is the number of photons, or number of, we'll call them photons, right? A photon is a light particle. And these are the frequencies of the light, of the photons. And h is a constant. Okay, so that's really interesting. Now we've already we have something, the energy of a light field has something to do with its momentum. Right? If you think about it as think about a wave, and when it hits you, right, the faster the larger the amplitude of the wave, the faster it's moving, the harder it hits you physically, right? Think about like an ocean wave, right? If you have a little small wave that's kind of meandering down the ocean, that's kind of low amplitude, it hits you, you barely feel it, but you'll feel a 12-footer moving at 10 meters per second, right? That's going to slam right into you. Right? So you can kind of have a logical sense of how the momentum of a wave is associated with its energy, how fast it's moving as it propagates. But what Max Planck says is that the energy of this wave is also, again, some function of its frequency. So that means that light has both a frequency and a momentum. And so de Broglie realizes that you can put these things to these relationships together. And de Broglie says that the momentum of any quantum mechanical particle is equal to this constant h over its wavelength. So let's think about what this means. So if you have a particle that's moving very, very fast, so let's think about one of you, for instance. So let's imagine that we're thinking about the momentum of you running, right? So let's say let's just keep the numbers simple. Let's say you're 100 kilograms, which is my size, probably not most of you. 100 kilograms, and you're moving 1 meter per second, which is about that's just about a stride, right? The momentum of that is 100 kilogram meter per second. And so we could calculate the wavelength of you as a particle if we know the value of h. we can start to think about that for a second. So let's think about one of you running, or a runner running at 1 meter per second, 100 kilograms. Do we see wave-like properties for that person? No, of course not, right? Human being is a particle. So what does that mean? Well, that means that the momentum is really high. Then that must mean that the wavelength is really, really minuscule, right? The wavelength is so small we don't observe it for a human. Okay. So h must be a fairly small number, right? So where do we start to see wavelengths, right? What mass scale do we start to see wavelengths that are, say, in the optical region, right? Think waves that we can actually determine, right? Things that we can measure with light, right? Light wavelengths. And you realize that the size scale, we'll see this, the size scale of the masses and velocities that are consistent with wavelengths that are say in the optical region or in the infrared, very, very small particles moving very, very slowly. So the only thing that really determines that, of course, is the size of this constant h. All right, on the next, maybe we'll do a fun calculation. It may be worth thinking about once we have the value of h. What is your wavelength? If you're moving, what's your wavelength? And you'll find that the wavelength of a human being is imperceptibly small. But if you take the mass of a human and say replace it with a hydrogen atom, right, 1 AMU, very, very small mass, you'll find that the wavelength of a hydrogen atom is very, very big. And in fact, if depending on the temperature and how fast it's moving, the wavelength might even be bigger than the size of the particle, which is very interesting. Right? So the thing is that wave and particles are both waves and particles at the same time. Whether their wave properties are dominant depends on the magnitude of wavelength compared to the size scale of the system. So let me explain that for a second. Okay, so first we need to come up with a value for this h constant. And this is my first law. And in fact, this is probably the most important thing in the entire class equation. It's called Planck's law. We've already seen it before. But it says that in quantum mechanics, so in QM, so for quantum mechanical particles, the energy of the particle, or of energy of the system, is equal to h times its frequency. E equals h nu. All right? This is a really, really nice equation because what it tells you, so let's think about the thing that naturally has frequency or wavelength, which is light, of course, right? So you can calculate, if you know the wavelength of the frequency of your light, you can calculate how much energy it has. Right? You just take its frequency and multiply this constant h. Now, what is the value of h? Well, h is defined exactly now in the SI units, so it doesn't have an uncertainty. So I'm going to write the whole thing down for you. We won't have to use all these values. But it is a very, very small number. So it's 6.626 times 10 to the minus 34 joule seconds. Right? It's a good number to write down because we'll use it all the time. Right? And remember, if you've taken thermo with me, we always use Kb, or the gas constant, right? The gas constant was our number, right? Because it allowed us to convert between energy and temperature. Right? That's what R does. R gives us an energy for a temperature, right? Planck's constant gives us an energy for a frequency. Right? It's the same kind of concept as R. It's a conversion factor between two measurements of energy. In this case, instead of it thinking about temperature and energy, right, thermal energy, here we're thinking about wave and particle energy, wave energy. Right, the frequency. The energy is dependent on the frequency. Now, this may seem strange because if you think about light, let's imagine. So let me imagine an example here. This might seem kind of odd to you, and in fact, it was very odd to the physicists and the chemists of the early 20th century, this equation, because what it says is that the energy is equal to the frequency of the light, and that's counterintuitive to how we understand how waves work. Right, so what if we were to, for instance, take a material? All right, so let's just take a sheet of metal, All right, I'm just going to draw, this is a little metal sheet, all right, with atoms. All right, so this is some metal. All right, and I'm going to shine light at it. So here's my light wave. And it has some amplitude. So do A cosine 2 pi v times t. All right, so it's a wave of frequency v. And it has an amplitude A. All right, and let's remember, so the frequency again is how fast the wave oscillates. And A is proportional to its brightness. Right, the brighter the light source, and I'll draw a little light bulb here. Right, you have a little light bulb here that shines light at this metal. All right, and we can turn the brightness and we can change its frequency. Okay, those are the two things we can change about it: how fast the light is oscillating, right? Its wavelength, if you will, or color, and its brightness. All right, and what happens when you shine light at this? If you shine it, what you find is that when you shine light at a metal, what happens is it kicks electrons off. All right, so when you shine lights, electrons kick. Okay, so this is what's called the photoelectric effect. Right, this is how, for instance, how a solar cell works. Right, you use light to excite an electron, and that causes conduction in your cell, your solar cell, and you can use that voltage, that current, to store it in a battery. Right, you're using the light, the energy of the sun to create a voltage, and then to charge a battery using the photoelectric effect. Right, and so let's think about this in like the most naive way. Right, let's think of our light as a particle. Right, we want to smack as many electrons off as possible. Right, so we're going to want to hit that. We're going to want to hit those atoms of light as hard as possible. Right, so what's the logical way to hit something with light as hard as possible? Well, just crank the brightness up. Right, if we see that there's a flux of electrons at a given light condition, we should be able to crank it up, crank it up, crank it up, crank it up. And we get more electrons out. And that should be frequency independent. Right? Because it doesn't really matter what frequency the light comes in, just as long as there's enough energy. As long as we hit it hard enough, it doesn't matter what the length of the bat is, we just got to whack it. Right? And so the brightness is your energy, effectively, of your wave. Right? So what would we expect? Well, if we were to plot on a graph, the frequency of the incoming light versus the voltage of the electrons. Do I have that right? Oh, sorry. So yeah, so the number of electrons that come off, we'll call it N E sub, right? The number of electrons that come off the metal is a function of frequency. Well, we know that at some point that if the frequency isn't low, and if the frequency is like, if the light is too soft and it's too infrared, it's not going to do anything, right? You know, we know kind of theoretically or implicitly that if you shine infrared light at a object, it doesn't ionize the material, right? In order to ionize an atom, you need to have high energy light, and we typically use UV light for that, right? A solar cell doesn't really work that well at infrared. It works well at visible and ultraviolet. There's some cutoff. So what would we assume? Well, so at some brightness and some frequency, there must be some natural frequency where it starts to kick in like this, right? And so we'll say that this is like a normal brightness. So normal A for amplitude. This is what we expect. Sorry, so it's expected. All right, so let's say we pick this frequency. We basically we're fixing the brightness and we're changing the frequency until we start to see electrons coming. Okay. And so now what we're going to do is we're going to turn the brightness up. Well, now you have more energy per unit light because your brightness is larger. You've got, well, sorry, you should think of brightness that you have more light. The amplitude of the light field is stronger, larger with a brighter light source. So you have more energy being imparted onto the metal per unit time or whatever. And so that would mean that the frequency at which we would expect that the electrons would start kicking off would be lower. Because now there's more energy per unit light, if you will. Because we've turned it brighter, right? We have more energy per photon, if you will, a higher amplitude. So it should start, the critical amount of energy should be at a lower frequency. So if we brighten it up, we would expect it to be something like this. This is bright. There's more energy per unit spot that the light is shining on because it's brighter. So you have more energy per unit surface area. All right, so you go and do this experiment. And let me tell you, people do it all the time. It's literally surface, like if you ever thought about solar cells or any sort of oxidation redox reaction, you think about these things, or photoredox, any sort of photochemistry, you think about these things. So this is the actual measurement. And we're going to plot the number of electrons we see versus the frequency. And again, I'll plot with normal A with purple. Like that. This is normal. But when you turn the brightness up, you don't actually see the intercept on the x-axis go to less frequency, but rather it starts at the same frequency. Now, because the light is brighter, you get more electrons. Get more electrons out, but the frequency that's required to start ionizing the material, start kicking electrons off, never changes. All right, so we would expect the expected result with what we understand about light in a classical way, right, in physics class, right, that the brighter the light, the more energy it provides. But in fact, what we see is that the only thing that it does is it increases the amount of electrons that comes out, but ultimately what determines the required energy, the critical energy for electrons to start moving, to be released, is the frequency that you choose, and it never changes. All right, so that means that the energies of the electrons, the result of this is that the energies of the resultant energy of the electrons, is not proportional to brightness, but is rather proportional to frequency. So it's proportional to frequency, not amplitude. Okay, and so Einstein, one of Einstein's great papers from I think 1913, he published 3 major papers. One of them was on this, the photoelectric effect, and he has a very, very, very simple explanation. So he says this. He says that let's measure. How do we measure how much energy an electron has when it leaves? Well, we measure its kinetic energy. So what we're going to do is we're going to measure escaping electron kinetic energy. Okay, and what he says is that the kinetic energy of the escaping electron is equal to this h nu, right? This is the energy of light, right? This is what Planck says. It's the packet minus this function called the work function. And you can think of this as how much energy it takes to take an electron off, right? So this is the W is called the work function. Or you can think of it as the binding energy of the electron in the metal. Right? Or you can think of this in terms of, if you think about the periodic table, this is the ionization energy of this material. Right? So for instance, if this is hydrogen metal, or a hydrogen gas sample, instead, we're doing photoelectric effect on hydrogen gas sample, work is equal to 13.6 eV. Right? This is how much energy it takes to remove an electron from a hydrogen atom. So what does that mean? It says, well, if we shine light, if h nu is less than 13.6, then the kinetic energy of the electron will be negative, which of course doesn't make any sense, right? So that means the electron's there. There's not enough energy to remove it from the metal, right? And so then we crank up the frequency of our light. We go to higher and higher frequency towards the ultraviolet. And we get to the point where h nu is equal to W, where our light frequency or our light wavelength is equal to 13.6 eV. And then the electrons start coming off, but they come off of zero kinetic energy, right? That's the point on our plot. This is the point on the plot right here where we have just enough energy to remove the electron. So the electron takes that 13.6 eV. That's enough to get it off the metal. Now it has no energy left. It's got no kinetic energy. So what happens as we start to crank the energy up more and more, or the frequency of the light more and more, make the wavelength shorter? Well, then the electron will have an excess of energy because h nu is greater than W, and then the electron will come off with more kinetic energy. And when you look at what that means is that the kinetic energy, if we were to plot kinetic energy on a plot versus frequency, we'd get a straight line. So if I were to plot here frequency of my light versus the kinetic energy of the electrons as they escape, at a frequency of the work function divided by h, you now have electrons with positive kinetic energy, and you have a nice line. Let me draw that straight. Sorry, guys. Like that. Right? The electron does not leave. There's no electron until you hit that critical amount of energy. And what's the slope of this line? Well, the slope is h. Right? So you can actually, so people actually do this. They go take a material, hydrogen gas, and you shine light at it as a function of frequency. You tune the light of the color of your light until you start to see electrons come off. And then you keep tuning the light and see how the kinetic energy changes as a function of the frequency. And you get a beautiful straight line, and the slope is h. This is how they determine h. Well, it's one of the classical ways they determine h. Right, so when this experiment was done in the 1910s, as a part of, I don't remember who did the experiment, but part of Einstein's study, they did this experiment and measured this. You measure the kinetic energy of electrons by, for instance, time of flight is the way we do it now. We have a big long tube. We know when the electron was created, and we measure how long it takes to get to the other side. We know the length. We know the length. If we know how long it is, and we know how much time it is, we know how fast it's moving, so we know its kinetic energy. Right? So as long as you know the distance that the electron is moving, you can calculate its kinetic energy. And we get this beautiful straight line in h. Right? They calculate h. Einstein and his experimental collaborators calculate h to like 1% in 1910 before this study. Right? It's a very, very impressive experiment. If they could get this really, really small constant, a tiny number, 10 to the minus 34, and they could do it with 1910's technology. Okay, so what does this mean? Well, this means the electron, wow, the electron has a kinetic energy, right? We can detect how fast it hits our target, right, our detector. When it gets released from the metal, we have some detector at some distance. We can measure how long it takes, right? So we have a trajectory for it. It acts like a particle when it leaves. But its energy properties are wave-like, right? It responds to the incident radiation as if it were a wave, but we detect it like a particle. Okay, so the only way to describe both of these results is that the electron must be a particle and a wave simultaneously. Right? That it has to have both properties. What we're going to find is that this is absolutely true, but it's even worse. It's much harder than that. It's not that it does have both particle and wave properties, but not simultaneously to us. We have to choose which way we want to think about it. So depending on the context of our experiment or our measurement, the electron may very well look like a wave and act like a wave. But if we do an experiment like, say, we're ejecting an electron and we're waiting to see how long it takes to go from the source to our target, and we know it has some kinetic energy, we're treating it like a particle. Right? And it turns out you can't do both at the same time. You can only do one or the other. Depending on the context of your measurement, you get one or the other properties. So it's not, so in some ways the electron is both, but it's also neither, because it will never exhibit both properties. It will exhibit either or, but it's also both of them simultaneously. Right? So we will only ever see one or the other, but the particle, before we ever measure it, actually exhibits both wave and particle duality. Right? That's what we just saw here. Right? It does both, but it only does one at a time. And that's not a limitation of the electron. That turns out to be a limitation of us. Limitation of our measurement. It's a failure of our part. When you do the homework, you'll realize that color and flavor are not compatible measurements. If you know the color, you don't know the flavor. Now, electrons have flavor and color both. But if you know one, you don't know the other. Right? So our definition of the electron is contextual. Right? We have to choose which way we want to think about it at a certain point. And that makes us lose information about the other option. And that's the same for weight, for position, or our particle and wave properties, right? Frequency and wavelength versus momentum and position. Momentum and position we'll call our conjugate. You can know a lot about position. If you know exactly where your particle is, you know nothing about its momentum and vice versa, right? And that's wave-particle. A wave has a momentum and a particle has a position, and you can know one or the other either. Right? So that's what we mean by duality. Is that it exhibits both properties, but we have to choose which one we prefer. Right? Depends on our context. That can be a good thing, because sometimes maybe we want an electron to act like a wave. Sometimes we want to act like a particle, and it can do both for us. We just have to prepare an experiment that gives us that. Okay, so this allows me. This is kind of a little bit of a background, but I think it's an important one. E equals h nu is perhaps the most important equation in this class, maybe the second most important. And it's important to think about where it comes from. And it comes from the fact that particles that have kinetic energy, particles that have definite position and motion, they also have wave properties, and we can relate them. We can relate the energy to its frequency. Any questions so far? Okay. So we're ready for our first postulate. We now have to, the first thing we want to define is, how do we represent a particle in our language? Well, what is an electron? And if an electron and an atom and a molecule, they all have the same properties, they all have the same kind of behavior, we have to have some sort of object that can represent all of them. Right? Some sort of generic particle object. In Newton's physics, the way that we define a generic particle is we give it a mass, we give it a position, and a momentum. Right? So we have to come up with something like that for quantum mechanics as well. We have to have some definition of a system. And that's going to be our first postulate. And postulate 1 is the wave function. Probably heard of it. Right? The wave function will be our generic object. We'll have a wave function for an electron. We'll have a wave function for an atom, for a molecule. Right? And they all share the same properties. They all share kind of the same features. But of course, they represent very different things. Okay, so I'm just going to write some text here and talk about it. So a state of a quantum mechanical system so what I mean by state, it could be like, say, a white electron or a black electron, but it could also just be an electron. All right, so think about state as particle, but it could be more specific than that, specific type of particle, say a white or a black one. So the state of a quantum mechanical system is completely specified, completely. It's the only thing we need to know about. If we know this one wave function, we know everything about the system, completely specified by its wave function. Right. Let me clean that up a little bit for you. The wave function of the particle. All right, and a wave function, we have a notation for it. The wave function, we use the Greek letter psi, which looks like a pitchfork. All right, and it's going to be a function. In our case, it can have different variables, right? It's a function, so we got to put something in it, like some position or something. In our case, we're going to represent it in position space. It's a function that takes in r and time. Right, because we might want to consider how the particle propagates or what it does in time. So we got to think about it in time as well. Right, so this is the wave function. Right, and r is an xyz vector. Right, it's the position of the system in three-dimensional space. Oh, sorry, that's z. I apologize. Oh, sorry, that's k. Sorry. Maybe you remember this vector notation, right? So we're going to want to simplify this. We'll do things in one dimension, right? It'll be just a function of x. All right, but we're going to, when we get to the hydrogen atom, we're going to do things in 3D because a hydrogen atom is three-dimensional. It's a sphere, effectively. So we got to consider things in 3 dimensions. Right? And we're going to want to think about, so for instance, let's again consider our electron bound to a proton in a hydrogen atom. The electron can be in 3 dimensions around that, right? It's spherical, and it also moves at time. Right? So our system, our electron, is going to be defined by a position and a time. Right? And the wave function has some properties. It has 2 big properties. One is very scary, but we'll get around the scary property. So the first property of it is that the wave function is complex valued. Right? That means it's not real, it's complex. It has, so you can think of, if you put in a value psi of r of t, just from t or psi, this is going to be some complex number a plus bi. It's a complex number. Right? I'll explain why it has to be a complex number in a second. So this is, in fact, why complex imaginary numbers are so important, is because things in real life can actually be represented by complex numbers. This is where it shows up. Quantum mechanics and waves. Waves are complex. So we have a wave. So if you plug in a value r and a value t, you're going to get a number out, a given position, a given time. That's going to be a complex number. Now that's scary, but it turns out that that's very, very useful, and I'll explain why it has to be complex. The reason why it has to be complex is that wave function is normalized such that the integral over all space, so dr, right, we're going to integrate over all space of our wave function, of the wave function squared, the absolute value, the magnitude of it squared, is equal to 1. Equal to 1. Okay. So every wave function is going to satisfy, we'll talk about what it satisfies, but the number one priority that it satisfies is that if you square it, you take the magnitude of it, it's got to be a magnitude because it's a complex number. Well, I'll talk about that in a second. But just imagine it's a real number, it's a real function, it's just a normal function. When you square it, when you integrate it, it has to integrate to 1. Right? So it can't integrate to infinity. It has to integrate to a finite number. And in particular, it's going to be set such that it's going to integrate to 1. Right? So what does that mean? So basically, that means that the function has to be continuous. Right? It has to be continuous and smooth, which means that it can't have any little cusps or anything like that. It has to be a nice continuous function. And of course, it means it has a convergent integral. Convergent indefinite integral. Right? That it can't diverge. Right? That really limits the number of possible functions that give us that. For instance, I'm just going to write it on the board, just as a simple example. Right? We'll have to start thinking about what functions satisfy these properties. But for instance, let's imagine I just, for shits and giggles, I just think it's a linear function. Okay? So what's I squared here? Well, it's bx plus c squared, which is 2bx squared plus 2cbx plus c squared, something like that. And if I integrate this function, right, if I integrate this function from negative infinity to infinity, that's all space, it diverges, right, because the integral of an x squared function is infinite. So this can't be, right, a wave function can't be a line. Right, this is infinity. Well, let's go from 0 to infinity. 0 to infinity. Right? If you integrate from 0 to infinity, this function goes to infinity. Right? So this can't be a function, right? A wave function cannot be a line. Right? So there's only a certain class of functions that satisfy these properties. Right? So the question is, of course, what? Well, it will depend on the system, but we can come up with a generic situation. And this actually, if we think about what's a generic function that satisfies these properties, that it's complex and it integrates to 1, you can actually come up with a really simple explanation. So let's think about this for a second. So remember I talked about wave-particle duality just a few minutes ago when I said that if we think of a particle in terms of its position, right, which is like, it's moving in space, and we think about a particle as a wave, an object is a wave, right? A wave is distributed across all space, right? So what is a wave? Right, so the idea is that let's assume that a particle has a defined momentum. All right, we know exactly how fast it's moving. P naught. All right, so what's a wave? What's a good function for a wave that has momentum p? Well, we can write our wave function for this system at our given momentum as a function of x. It's going to be a cosine 2 pi p over h times x. All right, our frequency is equal to p over h. All right, so if we draw this in our coordinate system, what does this wave function look like? I'm sorry. Well, it just looks like a sine wave, right? It just looks like a cosine wave. So this is psi of p here. Oops. So our x-axis is psi of p. And we plot it versus x, right, this is what the wave function looks like. Okay, and so let's think about what this means in terms of the position of the electron. Okay, so this is the wave function for its momentum as position, but we know that if we know its momentum exactly, right, we know its wave property exactly, we know nothing about its particle property, its position. So what does that mean? So if P is well defined, and that means position is not defined, right? That means the position of we have no knowledge of the position of the atom. All right, so the question I want to ask now is what, so let me go ahead and plot this. What is the probability that if we put a detector at any position, what is the probability that we'll observe the electron at that position? All right, so we take our detector, we put it at random positions on our line, and we say, what's the probability of finding it here? Well, if we know nothing about the position of the electron, we know nothing about its particle behavior, it's a pure wave. The particle can be literally anywhere, right? The probability is equal at all positions. Right, so the probability that we expect for the particle of the wave, so we'll call that the probability of observing the particle at position x, should be a straight line, right? Because we know nothing about the position of the particle. Right? It could be anywhere, and it's equal opportunity. Right? So the probability should be a flat line. Okay, so the question now is how do we measure the probability of finding, given a wave function, how do we measure the probability of finding the particle? Well, the first postulate, let me go back to the previous page. How much time do we have left? Good, we have a little bit of time left. Sorry, that's the wrong page. I apologize. So if we go back to the previous page, this normalization condition, it says here that if we square the wave function and integrate over all of it, right? We're going to integrate under the entire curve from the bounds of our laboratory, if you will. Like the x-axis is our laboratory. It says that the integral is going to be 1. Right? If you think about 1 as a probability, right? It's like a 100% chance. Right? That what this means is that over all space, our particle has a 100% chance of existing in it. That's what this means. That the total probability is 1, and if we look at the probability of where our molecule is, our atom or electron is, which is psi squared, when we integrate over all the possible places it could be, the probability of observing it in any position is 100%. Right? We're going to observe it eventually if we look in every spot. Eventually, it's going to show up. Right? That's what this means. So, in fact, what we're going to interpret is that this object psi squared is the probability of observing the system or the particle at position r and time t. Okay? So psi squared, the square of the wave function is its probability. Right? We'll see this so much in this class you'll get sick of it. Right? So if it's not clear yet, we'll make it clear. Right? So this psi squared, this function that we're integrating, is something to do with the probability of the particle being at some position in time. Right? And so when we integrate over all positions, the particle's got to be there somewhere, so the probability is 100. The chance is 100%, or the probability is 1. Right? That's why it has to be normalized to 1. because if psi squared is the probability, there can only be a probability of 1 to see it anywhere, or 100% chance. So this number has to be 1. Right? Just physically, that's what we normalize it to. So this psi squared tells us something about probability. This is called Born's rule, the Born interpretation. But it's the most important part of the Copenhagen interpretation, this set of the postulates we're talking about, is that what we actually measure is probability, and we do it through taking the square of the wave function. All right? Psi squared tells us lots of stuff, as we'll see. So let me go back to the next page where we were discussing this. Right? So we would expect now that this isn't the probability of x, but rather it's the square of the wave function. This straight line is psi squared. Right? This is what we want. Right? This means that the particle can be anywhere. But we've already defined a wave function for a system of definite energy. Right? So this is our wave function, so if we square it, we'll get the probability of finding that particle at a given position x. So what's psi squared here? Well, that's super easy, right? We just square the a, right? So psi squared of RT, let me just write it like this instead. Let me be more careful about this. Squared is a squared cosine squared 2 pi p over h times x. Right? We just square it. So what does that function look like? Well, it's the square of a cosine. So it oscillates between 1 and, well, a squared and 0. So this wave function doesn't work because when we get the probability, right, this says the prescription is that when we square the wave function, we get the probability of observing it at a given position x. That's what psi squared tells us. But this gives us an oscillating function, right? So this tells, right, if this is our wave function, the psi squared for our particle, this oscillating function, it would say that there's a very high probability of seeing it here at the peaks, and there's no probability of seeing it at the troughs. Right, so this is high probability, right? So this is at a squared, and this is at 0. Right, so that must mean that, and with this wave function, if our electron or our particle is associated with this wave function, then that must mean that the probability of observing it somewhere changes as a function of the wave function. Right? There's parts where you don't see it and parts where you do see it. Well, that contradicts our assumption. Our assumption is that if you know its momentum, you don't know anything about its position. You know its wave properties, you know nothing about its particle properties. So we would expect this psi squared, a straight line. So this function can't work. Right? It doesn't work. It doesn't give me the right square. All right, so what is a function that gives me the sinusoidal properties that I want, right? It's still a wave, right? It still oscillates at a frequency, but it gives me a straight line for its probability. So what do we need? We need psi squared to be constant valued, and we need the wave function itself to be proportional to a cosine. Right? We need both properties. We need it to be a wave that oscillates in space, and we also need to have a constant probability in space. So there's only one possible equation that works. So this is our wave function at a definite momentum and measuring it as a function of space. It's A right? Our amplitude times e to the I times p times x. Sorry, let me change that. Sorry. 2 pi I times p over h times x. Right? It's a complex exponential. Now, there's a nice rule. We can simplify this because this looks like an awful equation to do, but there's a really nice simplification called Euler's law. Which says that e to the ix is equal to cosine x plus I times sine x. All right, so a complex exponential is a complex number because there's an I in it, but it's sines and cosines. So we can rewrite this as a times the product, a times the amplitude of the system, times cosine 2 pi p over h times x plus I times sine 2 pi p over h times x. Right? So our wave function, again, still has sinusoidal properties, right? Here's the real part. It's the same wave function we wrote down. Right? This is the wave function we guessed first, right? This cosine. But there's also this complex component, the sine part, as well, that again has the same frequency, the same phase and everything, but it's on the complex plane instead. Right? That might sound scary, but but there's a really nice simplification we can do. And this is my last point. Right, so this is a complex wave. We'll talk about what it means to have a complex wave later. All right, so but bear with me. We'll kind of think about this a little bit differently soon. So it's a complex wave, and so now the question is, so if psi of x is a e to the I 2 pi p over h times x, what is psi squared? Well, when you take the square of a complex number, so if psi is complex, psi squared is equal to psi, which I'm going to call star psi, and this star is called the complex conjugate. And it's really easy to calculate complex conjugates. So if psi is equal to e to the IPX, then psi star, all you do is you take the negatives, the i's, and make them negative. Psi star is going to be e to the minus IPX. Okay, so anytime you see this complex conjugate notation, that means you're going to take all the i's and flip the sign. Right? So if, for instance, if m is a plus bi, a complex number, then m star is a minus bi. Okay? The reason why we do this is that means then that psi star psi squared, is going to be a squared, the complex conjugate of e to the 2 pi p over hx is just minus that, e to the minus 2 pi I p over h times x, times the wave function originally, which is just e to the 2 pi I p over h times x. All right? And so what do we have here? Well, we have a squared, which is just a number, just the amplitude squared. And then we have e to the minus something times e to the positive, the same thing. Well, these cancel each other out, right? Because e to the x times e to the y is e to the x plus y. And we have e to the minus x plus times e to the x. So we have e to the minus x plus x, which is e to the 0. Right? They cancel out. The complex part cancels out. And so that means that psi squared, what we measure, is just a number, a squared. Right? That's exactly what we want. Right? We said that if the system is defined at a specific momentum, right? It has a specific velocity, and we know nothing about its position, right? If it's a pure wave, which all wave is a particle, something that's propagating in space that's completely delocalized, but it has a fixed energy, a fixed amplitude, and a fixed momentum, equivalently. And we said that because it has this, we know nothing about its position, right? Because a sine wave is extended over all space. Right? It's got troughs and all over, from negative infinity to positive infinity. It can be anywhere. But because it can be anywhere, that means it has to have constant probability to be found at any point. Probability can't change to observe it. So we must have the probability must be constant for the right wave function. And the only way to get that is if our wave is complex. All right, so quantum mechanics this is my take-home point. Quantum mechanics, quantum particles, quantum systems are necessarily complex or imaginary. I hate the word imaginary for this reason, because imaginary implies they don't exist, but they do. You just have to use a different coordinate system than just normal space. There's some other motion going on that's moving in the complex plane, right? And this is just what happens with waves, right? Waves are complex. They have a wave has two components. It has an electric field and a magnetic field. They're both perpendicular to each other, right? So you have a wave propagating in this way and a wave propagating in this way. And the only way to represent that properly is to do it on a complex plane where the phase of the wave is moving in a circle in a complex plane. This way it goes in the phase, right? And so particles are the same way. You have to have complex numbers for this. And so this idea that when we square a wave function, our probability, it's going to be the complex conjugate of the wave function times the wave function itself, so psi squared. Now, when we get to talking about the hydrogen atom, for instance, or say any particle, we're not going to worry about complex numbers, right? Because if we're thinking about the probability of observing an electron at a certain position, obviously that can't be complex, right? You have to get a real number out, right? Because you can't have a complex position. Right? It's a real position in real space. So there must be some way to get rid of the complex numbers. And that's what we do here, right? Psi squared. Right? And what we'll find starting next class is that psi squared is what we actually measure in class, or in lab. Psi squared is our connection to the wave function. We can't observe the wave function directly because it's complex. But we can measure the square of it because that's necessarily real. Right? So psi squared is going to be our connection to the quantum mechanical world. It's going to be our macroscopic projection of this microscopic process. Right? It's a necessarily real value that we can measure of something that's complex. Okay? So that's our first postulate, that we have these wave functions. And I'll restart it for you guys next class, which is that we have these wave functions. The square of them represent the probability of observing the system at a given position, or part of its coordinates. And that therefore, because psi squared represents a probability, the probability of observing the particle anywhere has to be 100%. Therefore, the integral of the probability has to be 1. Right? We call that normalization. We'll pick up from there on Wednesday, guys. Have a good one.